Okay, so yeah, I hope this is not too scatterbrained. So I'll talk about GLMs, probably one of the more widely used functions in the R language. And you're going to get a little bit about how they're implemented and some of my own biases about how they should be implemented. And almost all of this research I've been doing over the last couple of years in preparation for our book, which is coming out this summer. So this is a book that I wrote with Taylor Arnold and Mike Kane. It just went to the publisher this month, actually. That's the cover. And it should be out in the spring for the fall semester. It's a textbook. And it's got all kinds of stuff. There's a big chapter on linear models and on generalized linear models, but there's stuff on neural networks and all kinds of things about machine learning and statistical learning. And the emphasis of this book is very computational. There's reference R implementations of every algorithm in the book. So look for that. Before we talk about generalized linear models and what they mean, I need to define what a linear model is. Every once in a while, there are going to be some slides with math that you could just ignore if you don't like to look at the math, because there will also be slides with R that correspond to the math. It's hard to prepare talks like this for like a super general audience, and it's also hard to talk about this topic without getting into some of the mathematical subtleties, because that's where the really interesting stuff is. So just don't try and, if anything confuses you, interrupt me. Oh, shoot, sorry about that. Okay, came back. So yeah, if anything confuses you, just interrupt me and I'll try to explain it. But what I mean when I say the word linear model inside of that larger phrase, generalized linear model, is that we've got some data that somebody gave us. We'll call it X, and we want to estimate, and we have some measured values Y, and we assume that the changes in Y that our model produces are proportional to the values in X, regardless of where you are in the data X. It doesn't change. That's what the word uniformly means there. You guys already intuitively know exactly what that means. It's a freaking line, right? That's a linear model, right? You've got some data along the x-axis here, and the measured values along the y-axis producing these dots. For example, this is just from some random R unif in R. And we run a line through them, and that's a linear model. It can be in higher dimensions, and you get planes and things, but they're always straight, right? The change, what I mean when I say uniformly is the change in this unit between -1 and 0 here is about 0.6. And the change in this line between 0 and 1 is also about 0.6, right? It's always the same. That's linear. Yeah?
You would not, okay, I guess you are going to talk about quadratic.
Not quadratic. I won't, well, a little bit, yeah. But this is nonlinear. This is, I don't know, this is actually an exponential fit, but it's not linear because the change in this unit is small. It's only like 0.25, and the change in this unit is huge, right? So it depends on where you are in the x value, how much the model changes. That's what I mean by nonlinear. Nonlinear problems are usually more complicated to deal with than linear ones. You've seen this in high school algebra, the formula for an expression of a linear model. Usually in high school you'd say something like mx plus b, right? So each y value is equal to a slope term plus a multiplier term times the data x, right? So instead of mx plus b, we've got b0 plus b1 times x. Beta 0. We're using x's and betas and y's because that's what all the stats textbooks tend to use. And if you've got a bunch of data, you can lump them together in this kind of a matrix equation, right? We've got a bunch of measured y values. I put hats on them because we're estimating, these aren't going to exactly reproduce the y values, probably. And then those are our exactly measured data values, x. And if you do matrix multiplication, you know, it's this 1 times b0 plus b1 times x, and then that's y1, and you just keep going down like that, right? So it's just the regular, if you don't like matrices and vectors, then you're kind of out of luck, because you have to use them when you use R to do anything productively. So if you don't know about or like vectors and matrices, you should really learn about them in order to use R and Python, for that matter, productively. And so here we can avoid all those subscripts and just write everything together as a vector times a matrix, x times b equals our estimate of the measured data y. We do a lot with matrices. We have to, actually. I know you may be confusing sometimes, but that's this game. So anyway, linear model. I didn't say, like, you know, these are all linear models, right? That was the same plot as I had up before. And all those colored lines are lines. They're all linear models for those data. Some of them might be better than others, right? But they're all valid linear models. So there's you know, you could imagine an infinite number of these linear models. And you know, the question arises, what's a good linear model? And there are many answers to that question, right? I can't give you a definitive answer, but a good all-around answer is this very famous thing that you've probably all heard of, ordinary least squares. And that's where, you know, from your measured data points, you drop lines vertically to the fit. And then you you add up all the squares of all these distances. Whatever that distance is, you square it, add them all up, and you try and minimize that quantity. It seems complicated, right? But there's a reason for that. And the reason, well, we'll see the reason over and over again, but the reason is that we get the answer in this form. And those double bars are just a special math notation for a function of the vector inside of them. And that's a very, very specialized function that has a lot of easy properties. We can work with it and manipulate it computationally very easily. So one reason why ordinary least squares is so widely used is because it's easy computationally for us to deal with. This is all familiar to you guys, right? Is this unfamiliar? Am I sounding like a stupid person telling you about all this basic stuff? It's important, though. So this is old, right? This guy, Gauss, was the first person really to formalize this idea at around 1800. But he didn't invent it. He was just kind of extending ideas from Legendre and Laplace, very famous mathematicians of their day in the late 1700s. It's interesting, actually. Remember I said this least squares, which Gauss came up with, we take the squares of these things and add them all up. Legendre, who preceded Gauss with these models, actually used the absolute value, just the absolute value of these distances and added those up, right? And that's also an interesting form of regression that's related to the lasso penalty, which some of you may be familiar with. So these guys back then, they knew a lot about this stuff, even though it was all new for them. They were very inventive people. And so Gauss wrote about this stuff. Gauss was very famous, and he did a lot of amazing things. Probably one of the smartest people ever, or at least on paper. But a lot of what he wrote about kind of got forgotten about, and this Russian guy, about 100 years later, Andrei Markov, reinvented this least squares, ordinary least squares concept in a very independent way from the way Gauss did it, and they came up with the two of them are credited with a very important theorem. Do I have this in here? Yeah, oh, I say it there. So these two guys came up with this famous Gauss-Markov theorem, which it's got some subtleties to it, but the gist of it is that in a very broad sense, this ordinary least square solution is the best solution. where the word best is kind of, you have to be careful when you define this word best, but it's a very generically best, good solution. And it works in many cases, independent of statistical distributions. And so that's a kind of a seminal result in statistics. Of course, neither of these guys were statisticians because that field didn't exist when they were working on this stuff. Okay, there's a little bit of math, and we'll get through that, but I go through this, here's some basic linear algebra stuff, matrix theory things, because this is kind of the core concept of how the R language and S language and Python and MATLAB and many other languages solve least squares problems. We're trying to figure out a value for those coefficients in beta. In order to know about that, we have to know about this thing called orthonormality, which just means perpendicular geometrically, right? If you have two things that are at right angles to each other, they're perpendicular. And that's precisely what the word orthonormal means, except orthonormal generalizes it to higher dimensional spaces. And if we have a vector y, like our measured vector, and we have a bunch of, so y has n components in it, there always exist these n special vectors called basis vectors, so that you can write y as a sum of these, you can kind of decompose this vector y into a sum of these parts. This looks all so formal and mathematical. It's really intuitive, right? Because when you plot, like imagine a 2D plot, and you plot a point, those coordinates along the x-axis and y-axis, those are basis vectors, right? So, if I say the x value is 1 and the y value is 2, then this gamma 1 would be 1 and the gamma 2 would be 2, right? That's the whole concept there. They don't, if they aren't the unit basis vectors, like you would plot values on a scatter plot, these q vectors are just rotations of them. They're always perpendicular to each other. The most important thing about orthonormality is you can decompose the length of a vector. Normally, you don't get this type of an expression. There's this famous inequality called the triangle inequality that even the Greeks knew about, that in the case where you have perpendicular values, you actually get an equality there, not a less than or equal to sign. Then if we assemble the data as we did before into this matrix, we had a 2-column matrix with 1s and then the data values x. And any matrix x, no matter what its dimensions, can be decomposed into these factors, q and r, where q is just a matrix whose columns are basis vectors, right? And then R is a matrix that's half zero. It's just an upper triangular matrix. I'll get past this right now. This is the last bit of this linear algebra stuff. But this stuff is actually, this QR decomposition is central to how R solves these problems, and MATLAB, and Julia, and Python. So it's kind of a super important decomposition. The most important decomposition is one that I won't talk about other than to mention it here, and that's the SVD. But this is another super important one that you need to know about if you want to know about how GLMs are solved. Okay, some horrible stuff. But this is the solution of just a regular linear least squares problem mathematically. We're going to see it in R next. But this is how it works in math. We want to, this was, if you remember, this we had on the other slide. This is this minimization problem. We want to have a model that fits our data as good as possible. We want to sum up the squares of these distances and get that number as small as possible. Find what coefficients make that thing as small as possible. And so you rewrite it with all this gobbledygook using these orthonormal bases, and you split it into these two problems, two parts. There's this part over here that involves our coefficient, and this other part of our data vector y that doesn't have the coefficient at all, and there's nothing we can do about that. That's going to be the error in our linear model. We have no lever to control this. It's just a constant. But this, we can modify the beta and make as small as possible. And the cool thing about this expression is this is really easy to solve because R is triangular. It's got zeros below the diagonal and possibly non-zero entries above it. And so that, you learned in high school how to solve those problems. That's this back substitution thing, right? Where you start at the bottom and you solve for the one value of beta, then you move up a line, then you plug that in and solve for the next value, and you move up. That's a very, very easy problem to solve. Computers can solve that one like that. So using this clever decomposition, we've turned our problem into something that's very easy. And just to prove that that's real, that it's not just a bunch of crazy math symbology, here's an example just in R. We make a matrix that's got 2 columns and 10 rows, and here's a vector y, so X is like our data model matrix. And then here's R's linear model fit function. So not a generalized linear model, but just a straight line fit for those data. And we get some coefficients for the constant term, the intercept term, and for the slope. And then here now we're using exactly what was on the previous slide. We form a QR decomposition of the matrix. We do a back solve, the back substitution like we learned in high school using the triangular matrix. And we multiply the data vector by the transpose of the basis. And we get the same coefficients, right? So that's precisely how, in fact, under the hood, that's exactly what this function in R did. It did exactly this, with some bells and whistles on top of it. But it's a really central and important decomposition for these problems.
See, Bryan,
Yeah.
what's the name of it?
The QR decomposition.
Oh, okay.
Yeah. Q is the basis, the matrix with the bases for columns, and R is the upper triangular matrix. I don't know why they use R's, but they use R. Okay, so that was linear models. That's the introduction. Now it just gets more complicated because we have to understand what a generalized linear model is, right? That was the topic of the talk. And this is the best definition I've found in all the literature for a generalized linear model. This is a definition from Peter McCulloch at the University of Chicago. And a generalized linear model is, it's 3 things. It's a linear model, which he calls the systematic component. And I like these names, actually. I think they're very, very nice. So you start with a linear model at its core, which is just like what we saw before. And then on top of that, you add this thing called a random component, which describes how the response vector's values are. It's a probability distribution that describes what you expect to be the expected values of the response vector, right? So we assume that they're distributed normally or uniformly randomly or as a binomial distribution or a Poisson distribution. But anyway, you have some concept of their distribution. This is, by the way, very frequentist. There's analogous Bayesian ways that are really exactly the same Bayesian ways of thinking about this, but I like this approach because it's so systematic. Okay, so we've got this linear component that's systematic, a random component describing the randomness in the measurements, and then there's this special link function, G, between the random and the systematic components. So we have this mu, which is just the expected value, the average value that we get from our probability distribution of the measurements. And then we have a function, G, that connects the linear part to that probability distribution. That's all a generalized linear model is. So maybe you don't want to hear anymore and I could just stop, but I could tell you a little bit more. So it seems, why not just stick with the linear stuff, right? It seems complicated. And so why introduce this complication? And there are many good reasons, but an obviously good reason for introducing this complication is this example right here, which I took from Wikipedia. So that's a self-contained little R code. You can copy and paste it and get this. So that's kind of a cool made-up example on Wikipedia of like hours of study versus the probability of passing an exam. So the idea is here's a bunch of X is a bunch of students who studied so many hours, and then Y is their measured pass-fail rate either 0 for fail or 1 for pass. And so when we plot those data, we get these dots, either 0 or 1, because the data are just zeros and ones. The y's are just zeros and ones. They either passed or they failed. And we can fit a linear model to those. That's the dotted blue line. It works, right? You can do it. Actually, in this is an interesting example because the linear model works reasonably well. It fairly well describes the data. If you think about the model instead of being pass or fail, but as a probability of passing or failing, it's not bad, right? If you kind of made a cut right at the midpoint of these things, a half, and said everything above that is gonna, everybody with a model value above that's gonna pass, and everybody with a model value below that's gonna fail, the linear model actually does a pretty good job of predicting the output in this example. Whereas the generalized linear model using a binomial distribution for the data, which is using R's GLM fit function right there, at the bottom there, that's the wavy red line. You know the name of that function?
Sigmoid.
Yeah, sigmoid, or a logistic. So that looks almost like the linear fit. It's very close, actually, in this example. But there's something glaringly wrong with the linear fit. Do you see what's wrong with it? Does anybody see like the horribly wrong things about it?
It goes beyond, goes higher than 1.
Yeah. We have probably. You probably all get this, right? I mean, the linear thing, it's just unconstrained, right? It can have probabilities greater than 1, which is nonsensical. Similarly, down here, it can have probabilities. If you only studied for 0 hours, your probability of failure is minus 0.3 or something like that, right? Which again it's nonsensical. It's not an interpretable value. In this case, you could shoehorn it into something that works predictively, but it doesn't, fit our model for the data, right? We expect a probability of success to be between 0 and 1 because probabilities are between 0 and 1. And so generalized linear models let us stick data inside of intervals, basically. That's their most basic utility, right? And not just intervals, but rays, right? We can also say we can only allow non-negative values, for example, if it's a Poisson distribution, like a count, right? You can't have negative counts, right? So if you're interested in positive counts of things, you need to make your model only on the right side of the real line. And so that's the basic use of GLMs. Does that make sense? You can put stuff in intervals or rays. The other kind of secondary use is that you can also give a much finer grained, you can equip them with a much finer probabilistic interpretation. You can pick from the random component, you can pick how you think the data should be distributed. And that can be informed by an a priori choice, if you're a frequentist, or from your data itself, if you're a Bayesian. In either case, the interpretation is the same. There's a technical thing. The random component, when we solve GLMs, for the most part, we don't allow any distribution in there. Basically to make things easy, there's a big assumption made there, and the assumption is that the distribution of the data fits into this thing called an exponential family. I'm not going to define an exponential family here because it gets to be fairly complicated. You can read our book if you want to learn about that, or McCulloch's book. But it's important to know that we kind of have an intentional limit on the scope of what we define to be generalized linear models. And a lot of packages in R, so you've used the LM and then the GLM function, and there are many packages like, for example, Frank Harrell's HMISC package, or Bryan Ripley's package that has a negative binomial in it. What's that package? And then, Mass, the book that goes with the book. And then the linear mixed effects models packages, there are several of them, various time series packages, they all kind of expand the universe away from this exponential family in little bits, right? But the core assumption of GLM is that we've got this special family. And it was the Fisher, the guy up there, funny looking guy with the glasses and the top, who first came up with this idea. He's a bit of a weirdo, by the way. If you've ever read about this guy, he was really into like eugenics and stuff. It was kind of creepy, actually. I didn't know that until I was doing some research for the book. But anyway, Fisher came up with this stuff using basically the example we had of the exams. It was it wasn't logistic. He was using a probit function, but it was this very similar type of example. He wanted constrained data to live in an interval between 0 and 1. And it wasn't until 72 that Nelder, with a lovely mustache, that's a great mustache, by the way, he came up with the phrase generalized linear model, and he was the first to define the exponential family to make things easy to solve. And then Peter McCulloch and Nelder together wrote this great book, which I should have brought with me. It remains the Bible of this from a computational standpoint, called Generalized Linear Models. And that book came out in '83. That was reprinted several times. It's a great book, very readable. And he's a teacher at the University of Chicago, McCulloch. He was Omar's PhD advisor, by the way. Omar sometimes comes to this meetup. And there are a lot of other people. Those are the three big names, but Green, Green, Wedderburn, Cox, Breslow, and lots of other people in mostly the 70s and 80s kind of fleshed out these ideas really nicely. And from our perspective in the world of R, it was these two guys that really did the most work for implementing GLM. And that's Rossi Haka and Bryan Ripley. And when you read the code inside of the statistics package for the GLM function, it's very faithful to the Nelder and McCulloch book, actually. Like, I mean, you can follow it almost one-to-one. The notation, everything is extremely similar. And Haka actually came up with some novel, when they were implementing this in the very early 90s, there were some things that they needed to do for edge cases that we'll talk about that he came up with this on his own that were very innovative. And we'll talk a little bit about that right now, actually. What time is it? Is it?
35.
Okay. Yeah, that's good. So how does R solve? So to solve a generalized linear model, first of all, what does it mean to solve a generalized linear model? This is kind of out of sequence. So here, this is the gist of what it means to solve a GLM. First of all, we have to formulate an optimization objective, similar to the least squares. We have to have something to shoot for, right? And generally speaking, we come up with this thing. It's somewhat mathematically complicated, but you come up with this thing called a minimum deviance residual, which at the end of the day is very similar to a nonlinear version of the least squares problem that we had before. It looks just like a least squares problem, except there's some nonlinear elements to it from that link function, G. Because the link function G is usually some sort of sigmoid or other weird thing, and it's not linear anymore. And so minimizing that minimum deviance residual is equivalent to maximizing the likelihood of the probability distribution that we're looking at. So there are two ways to think of a probability distribution. One is, here's my probability distribution. I expect my data to be distributed like this. The other is, given some data that I've looked at and some description of it from a probability distribution, what's the likelihood that I would have observed that data, right? And that's thinking about your probability distribution as a likelihood function, and you want to find the coefficients that make that most likely, maximum likelihood. I should point out there are many other ways to solve these problems, right? Maximum likelihood isn't the only way, but that's what R does in its GLM solver. And so there's this nonlinear G function, that link. that makes it, so it's kind of like a least squares problem, but it's got this nonlinear function stuck in there. And so you can't just get a solution quickly in one step. Instead, you have to use calculus, which I will spare you from almost all those details. And remember way back, you use calculus to find the optimum of a function. You take its derivative and see where it's 0, and then you look and see its second derivative if it's concave down or up, if you have a minimum or a maximum. You vaguely remember this stuff, right? And you have to use that stuff, right, to figure out if you've got the maximum likelihood, or in our case, the minimum deviance. And so you need derivatives of these functions. So like you look at the first derivative, and you try and get the first derivative to be 0. And you could stop there, actually, at this step. It's interesting, the R package doesn't do this. And in fact, I haven't seen a lot about this, right? But the neural network guys, they stop at step 3. They're like, screw this other derivative stuff. It's too complicated to compute those, so we're just going to compute the first derivative and apply gradient descent just iteratively over and over again. And that would work, actually. It will work, generally speaking, fairly slowly, but that's what neural network people do, and that's one reason why they're so slow.
Is that the same thing as automatic derivatives? Is that the right word?
No, automatic derivatives are a way to get the derivative. Like in our case, because we assumed a special form of the problem, this so-called, what did I call it? This exponential family of distributions. We know those derivatives exactly. We can, we have an analytic formulation of them. The cool thing about automatic differentiation, which is really just back propagation, if you're a numerical analyst, is that you can get those exact values of derivatives just using your data and your operator. But anyway, so you could stop there. And so the interesting thing about stopping at step 3, and this is something I'm working on now, it's an exercise in the book, but I'm actually fleshing it out, is that if you had some truly huge GLMs, or more complicated things like, for example, mixed effects models, that might start to look like an appealing computational approach. So that's a thing. Step 4 is never done, so we won't speak of it ever again. And then what R does is it uses a quadratic approximation to the function. So it takes a Taylor expansion, takes the first 2 terms, and that's called Newton's method. And then these guys, P.J. Green and John Nelder and Peter McCulloch, they when they were looking at the math, the calculus for this stuff in the 80s, they realized that it looked like a weighted, in some very special cases, not every case to be sure, but in very special cases, Newton's method has the exact form of a weighted least squares problem that's iterated over and over again. And they're like, well, that's kind of a nice way to look at it computationally. And so they called that the iteratively reweighted least squares solver, and that's what R uses. The special cases in italics there correspond to a special link functions. Each exponential family distribution has an associated link function called a canonical link function. And when you've got one of those link functions, then you're in this special case, and Newton's method is exactly the same as iteratively reweighted least squares. If you don't have a canonical link function, then they're different, and they may not. And basically, R only uses IRWLS. One open question for me that I haven't answered yet in my research is, are there pathological cases where this method doesn't converge? I don't know the answer yet. But I think it's just a poor approximation in general of Newton's method, and it'll converge a little slower, but it'll still converge to a solution. Because the gradient is still the same. It's the second derivative that's different. And that's the part where they differ. And when you get close to a solution, the second derivative doesn't become useful. So anyway, so here's the algorithm. This is like not one that you would actually use to compute, but it's the shortest statement of it that I could come up with. Remember, eta is this, the linear, the systematic component, right? And g of eta is G inverse of eta is the mu. G of mu is eta, right? Oh, that should be, sorry, that's LaTeX typo there. That should look like that n, that squiggly n there, sorry. So mu and eta are related by this length function or its inverse. By the way, the length function has to be invertible. In fact, it has to be more than that. It has to be monotonic. I didn't mention that. But so anyway, you guess an initial guess of the systematic component, and you just run this simple loop over and over again. And each step of inside of each loop step, you solve a regular least squares problem, but with a weight matrix, W. But other than that W, it's a regular least squares problem, just like we had at the very beginning. The only thing that's changed is this W, and the W is updated in each step. When you have a canonical length function, it's just the variance of the estimate, mu. That V means variance function from the probability distribution. So that's iteratively, it's a real simple algorithm. Yeah?
Is the diag the part of the triangle aspect?
No, it means a diagonal matrix. Just it's a W in this case. That's a good question. What does diag mean? It means, yeah, it's bad notation. It means W is a diagonal matrix. It has zero, it's all zero, except along its main diagonal, where it has these numbers, whatever they are, the variance numbers of the estimates mu. Right? So it's just got numbers along its diagonal. It's a really interesting question because of this next slide, actually. I'm glad you asked that. You may have heard of time series models like Garch or ARIMA, or others of you may, I know some of you use mixed effects models, generalized linear mixed effects models. They are both GLMs, and the only thing that's different between these two things and what we just saw is that they don't have a diagonal weight matrix. They have some other kind of weight matrix. That's really the only. You've wondered about like the mystery of these Garches and mixed effects. There's no mystery, right? It's just a different weight matrix. That's really all that's different between them from a computational standpoint. Obviously, there's some difference in interpretation. Okay, so what does R do? You can go into the stats package, look at the GLM function, and see that it has clearly marked inside the function the iteratively reweighted least squares loop, and it's very similar to that loop we just saw, with the exception that they use a very special, inside of each iteration here, they solve this problem with a bespoke QR decomposition written in 1994 by Rossi Haka. And he does that to handle edge cases. And it's called a rank revealing QR. And let's see, what do I say next? We'll defer discussion of that for just a few slides. But that they use a QR in each one of those to solve each one of the least squares problems in each step. Every time they compute a new QR decomposition. And by the way, McCulloch and Nelder say to do that in their book. It's interesting, in the Royal Society notices where P.J. Green wrote about generalized linear models in 1984. Have you ever read a Royal Statistics Society paper? Has anybody here ever read? There's this journal called of this organization of men that they all look like Fisher, by the way. That's I think, and they're all men. It's a precondition of being in that group, or at least they used to be. And it's really interesting the way they do it. These guys will write a paper, and then the reviews are published along with the paper. So the reviewers comment on the paper, and you get to see all of that in the journal. It's really interesting, right? So there's all this interesting stuff about, and actually it wasn't all men even in 1984, because one of the most interesting comments on Green's GLM paper was by a female professor at Warwick, I think, and she suggested using the SVD, which is what 30 years later, Mike and I did. Anyway, so here's an R implementation of iteratively reweighted least squares that's as basic as I can get it. This is, other than the special rank detection problem, the rank revealing thing, this is fairly faithful to what R does in condensed form. There's all sorts of bells and whistles to catch edge cases in R. But if you throw all that stuff out, at its core, this is what's being done. And you can see the thing I had up in math is like right here. Here we have a guess of eta, which I'm just initializing to be 0. Then we update it. We compute this weight matrix W. We solve a weighted least squares problem. And we update our solution, and we just go around. And so you can plug that in and use it. When I first saw this about 10 years ago, this disturbed me, this line right here. And then finally, about 8 years ago, I did something about it. And I'm like, there's no way that you have to compute that every time. And it turns out I wasn't the first person to come up with that. Diane OLeary, who's a pretty amazing mathematician. She's retired now at the University of Maryland. She wrote a paper in 1990, which is before Haka and Ripley wrote the GLM code in R, that show that you don't have to compute that QR factorization every time. You can compute it just once up front. And it's a really good paper. And here's her algorithm. It's a bit longer, but the change is that, and I'll put these slides will be online, so you can play with these. The change is you do a QR up at the beginning of the loop, and then inside the loop, there's no QR anymore. Instead, you have this Cholesky decomposition of which is another matrix decomposition of this thing, which is a very small matrix. So you're working on a much smaller problem inside of every loop. The upshot is that this is potentially way more efficient. Somebody emailed me about this, or GitHub issued thing about this to me about a year ago. And Mike and I we have this version, we have an SVD version. I'm returning to this version. But this is on the order of about, depending on the numerical libraries that you're using, this could be, and how many cores you have, this is going to be at least 10 times faster for large problems than the R implementation, and it could be much more than that, actually. And it's the same. It's mathematically computing the same thing. You can see in this toy example that the basic version, the Diane OLeary's version, and R's GLM version, in this toy problem of the Wikipedia example, can at least give you sensible, similar coefficients.
Right?
Yeah.
Is that method what the speed GLM package uses? Is that why it's faster?
No, the speed, yeah, the speed GLM package is something of a sad package in my opinion. So the basic, yes, so the basic deal with the speed GLM package is that, so there's a package on CRAN called speed GLM, and one of the unfortunate things about the custom QR used internally by R's GLM function is that it's written in some old Fortran. It's a modification of some old Fortran code, and it doesn't take advantage of a fast modern linear algebra library. Like, you may have heard of these things called BLOS and LAPACK, and it doesn't use those very well. So it's mainly slow on, one of the reasons R's GLM is slow is because of that. Speed GLM sidesteps that by using modern, by not doing the edge detection checks. They basically just throw away the corner cases, which is fair, because most of the time you probably aren't going to hit them, right? But if you but it can be numerically less stable, right? Like, or you could get into trouble with it, right? I find it to be a fairly sloppy implementation, in my opinion, but because you can do both, you can actually be numerically better than even what R is doing, and also faster, and I'll show you that. So yes, no, SpeedGLM is not taking this approach. It's basically throwing away the rank revealing edge case detection, putting in modern LA-PAC decompositions and solving it that way. And that is fine. That's what it does. And so it's a lot faster, right, for sure. But you can do better than that. And I was disappointed that the author of that package didn't. But why is that rank? Why is the special QR that Rossi Haka wrote important? And it's important because there are circumstances where you can get into trouble with these things. The two kind of common ones, imagine we go back to our 2D plots. If all the points are on a line already, right? Imagine that, right? We had our points, they were all scattered around, but imagine they all fell on a line. Then you could get into a situation where you have an infinite family of solutions to choose from. Or another bad example is where you have no solution, like you can't find a single solution at all. Both of these first two cases correspond to matrices that are called rank deficient, mathematically rank deficient. But there's a worse problem, and the worst problem is that the matrix is like nearly rank deficient. For example, the matrix might have two columns that are almost the same. That's a class, or a linear combination of many columns that add up to another column, almost, right, but not quite. And that's a really bad problem because it's hard to detect, number one, and number two is it makes your solution very sensitive to perturbations in the measurements. Like if you've got some errors in there, which you always do, right? And the errors could be from anything. They could be measurement errors. They could be sampling errors if you were doing like a survey. They could be numerical errors even if the matrix is ill-conditioned enough. So these are all very bad problems, and R goes to some length to try to detect those. But it doesn't always work. So here's an example. So Mike and I have an SVD-based version of that Diane OLeary algorithm that we've been tooling around with for a couple years. And this is a bunch of almost unreadable R code, but the point of it is the bottom line. So here we just set up a problem from start to finish. We build a matrix. We make the matrix pathologically bad here. Like we make one of its columns somehow dependent on the other problems. We also introduce some bad conditioning here by scaling the columns badly. This is like I carefully constructed this matrix to be evil for R. And indeed it is, right? So if we compute just a GLM fit, so first of all, if we leave the singular OK argument off, GLM fit won't even like it. It'll error out, which is probably the right thing for it to do. So in that sense, R is safe. But if you allow it to deal with ill-conditioned problems, R's GLM code breaks down. It gets a terrible. This is the error from the exact solution and what GLM computed. But our Diane OLeary modified routine still produces a stable solution in this case, and it does it much faster than R at the same time, right? So that's an interesting kind of counterexample for Ross E. Haka's special custom QR code. So here's another interesting thing. Let's say you have a matrix and two of the columns are nearly identical. What does R do in that case? Do you guys know what R does? Does anybody know here? You know, don't answer. Does anybody else know what R does? What would you do in that case?
Make a reference and an exception.
Well, it didn't used to. Before R 2.4, it did not make any. You had no clue that there was anything wrong. In R 2.6, Bryan Ripley changed that, and he flags certain things with NA outputs, the coefficients with NA, so that you know there's something gone awry. But, I mean, let's think about what you could do. What you could do is what you should do is if you have a problem, and so look, this comes up in problems where you have tons of columns, which is, these days in machine learning is kind of common when you have lots of columns, right? And what you should do for a linear model like this is you should throw the lasso at it, right? You should pare down your columns into something more sensible instead of trying to deal with this huge jumble of columns. You should pick a subset of columns that somehow give you the most information about your problem, and that's precisely what the lasso, or what's it called, GLM net is designed to do for you. But if you just throw R at it, R does something different. It's really interesting. R picks out, it does pick out a subset of columns for you, but not using any information. It picks them out in the order that the columns are presented. So if you take a problem, I don't have an example of this, but if we pick a problem where two of the columns are, oh no, this is an example. Here's a problem where the fourth and the third column, the fourth column, and the fifth column are all the same. They're all just the same column. They're repeated, right? But the solution I cooked up so that the first three entries of the solution are 1, the coefficients. So the third column is in the solution. And R's GLM gives you an exact fit, right? It exactly finds the right columns for you. However, this is exactly the same problem, except now here's our solution. The first coefficient, the second coefficient, and the fifth coefficient are in the solution. Otherwise, it's exactly the same. The data matrix is the same. Nothing else has changed. The only thing is the exact solution now is using another column. Then R's relative error is off the chart. It's as bad as it can be, right? And what R does is it picks the third column as part of its solution. It goes in the order that your columns are shown in the matrix, right? That's how it picks a solution. And I've had arguments with statisticians, and they kind of like this, but I find column order of matrices to be irrelevant as a mathematician. So it's kind of, I find this a weird thing, a gulf between stats and math, actually. But anyway, if you're in a situation like this, you shouldn't be using GLM. You should be using GLM net or something like the lasso. This is the wrong approach. So at least Ripley did a really good thing, though. In both of those cases, if we looked at the solution, we'd see that there are NAs in some of the positions. And if you ever see that in R, or you get one of its weird errors, like, you'll get this with the logistic that you have overfitted zeros and ones in your solution. If you get either of those situations, the zeros and ones, that weird error means that your data are all on a line. In the systematic component, they're all on a line. They're all the dots are exactly on the line, right? Which is kind of weird. It shouldn't be like that. And in either case, you've got problems, and you should look to another solution method. What I'm doing right now is Mike and I have an alternate solution implementation based on the SVD that gets around some of the weirdness of the internal R rank revealing QR implementation. We're still refining that reference implementation, but more recently, since I was working on the book, I got interested in actually trying to fix up the rank revealing QR implementation. And it turns out that when Haka wrote this in '94, there was an algorithm from 1990 by Tony Chan. At the time, he was at UCLA. Bill Gragg is dead, unfortunately. He, at the time, was at the Naval Postgraduate School. And Lothar Reichel, who was my PhD advisor, they came up with a rank, kind of the state-of-the-art, it remains the state-of-the-art rank-revealing QR implementation. Unfortunately, Haka wasn't aware of that code because it existed before he wrote the GLM in R, but he didn't use it. And I think that's the method that should be used internally in R. So right now I'm kind of on a kick to try to fix up the current implementation to use this, and this will both be more stable numerically than what we have in R right now, and also a lot faster. So that's one thing I'm working on at the moment. And yeah,
When you say it's written in R, do you mean it's written in, R or in that Lisp like R sublanguage?
well, when I say in R, these algorithms internally in R, GLM in R is the looping part. This kind of the program is written in R itself, and but where all the work is done, like if you do flop counting, almost all the work is in Fortran codes, or yeah, it's all in Fortran code. So, and that Chan, Greg, Reichel algorithm is also in Fortran. That's a TOMS 686 at the ACM TOMS library, but it's another Fortran code. Sadly, that algorithm is not in LAPACK, and it really should be, because it's a good one. Yeah, so so I'm kind of on a long-term mission. I've been thinking about GLMs for years now, mostly because of the book, but I'm on a very slow and steady mission to try to gradually improve how GLMs and mixed effects models and GARCH models are computed internally by the R and its various packages. Some things I left out that are really interesting, I think, are potential alternatives to the iteratively reweighted least squares, like using gradient descent or similar methods for super large problems. I think that could be, that if I were a grad student, that would be an interesting thing to look at. Because if you do a GLM by a neural network, you're using gradient descent, basically. And then this is a thing I didn't mention at all, but this is really a cool idea from Gene Golub. So when we analyze GLMs, we always think about error in the measurements. But you might have errors in your model data too, your model matrix, right? I mean, I worked at a chemical factory for a long time, and this was a common problem there. There are no R implementations I'm aware of that treat error in variables. The statisticians call that error in variables. The mathematicians call it total least squares. And it's basically where you just assume you've got error both in your model matrix and in your data. And it turns out that there are robust and good systematic approaches for dealing with that for linear models, but I've never seen them applied to generalized linear models yet. There's a professor at Utrecht in the Netherlands, Sabine van, oh wait, is she may have left there, but at one point she was in there. Sabine van Huffel is her name, and she's kind of the world expert on this approach. And I've been thinking about trying to expand some of these core R algorithms to deal with error in data. And then another thing, some friends of mine at Kent and Case are working on are lasso-like penalties, but that are better than the lasso, that get down to L0, basically. All of my notes are at this website, including these slides I will put up there. They're not up there yet, but the notes are out of date because I've been really stuck trying to finish the book. And so I've got a bunch of old GLM notes up there from like a year ago that are about to be substantially updated. So if you go there right now, it's just a bunch of old stuff. But in about a month or so, there'll be a lot of new stuff. But all those R codes are up there if you wanted to fool around with the toy algorithms. But yeah, so that's about all I have. That was a very mathematical talk. But that's I hope you learned a little bit about the good things and the bad things about GLMs in R. Yeah, questions? Anybody? You might have questions. I don't know. Ask me anything.
How many linear algebra courses would one have to take to really understand?
Just one. Just a basic introductory linear algebra course.
Just 101?
Yeah. The problem, okay, I have a beef with, look, I'm a mathematician, but I've never taught, other than, as an adjunct, I've never been I've always been in industry. And I think the way they teach linear algebra in college and high school sucks. Like they teach you determinants and all this useless crap. They should be teaching you the SVD, the QR decomposition, like stuff that you can actually compute with, right? Instead of this silly, goofy,
Well,
what's
it's pretty stunning to hear that. I thought determinants were like a
they're
basic thing.
totally useless. Theoretically, they're interesting, but they have absolutely no value other than in theory. Even theoretically, they're not that interesting. So they're really not that useful,
So
actually.
jump straight to SVD and
Yeah, get into matrix decompositions. And see, the other thing is, like, you spend a lot of time talking about eigenvalues. Eigenvalues aren't that useful either, right? These other decompositions, I mean, eigenvalue decompositions are also theoretical constructions, right? They're very, I mean, they're useful in some cases, but they're not that practical, right? So, yeah, but in principle, a single one semester linear algebra course is all you need to know. There's a great Dover book, which is like $5. It's by a Russian guy. It's called Lectures on Linear Algebra. And that's that's one of my it's theoretical, but it's also a very interesting and useful book.
So you need one course, but Bryan needs to write it.
I haven't written any. Yeah, I don't.
is that all you need for deep learning too?
Yeah, all this deep learning and neural network stuff, it's all linear algebra. Yeah.
All 101, none of this,
Yeah, all 101. Yeah. You need some calculus too, right? Because inevitably, like, what happens is you have these matrices and vectors where your data is inside of matrices are tables, right? You got these matrices. I mean, matrices are actually functions, right? They're functions that take a vector and they give you another vector. And, you know, your data look like matrices and vectors, though. And so that's the linear algebra part. But then you cook up real valued functions that, like this measurement with the sum of the squares, right? Where you get a single number out of it, and you want to minimize it or maximize it. You want to do something with that number. And in order, you know, whenever you hear the word minimize or maximize, that's calculus now. You need to take derivatives and, you know, so you need a little bit of calculus and a little bit of linear algebra for all this stuff, basically. And that's all, pretty much.
Thanks. You know, one thing that really interested me was when you pointed out that you could have the probability distribution, if I'm remembering the right words, and then you can transform it into some other form.
Well, it's actually the same thing. The only change is if you know, normally you would write a probability distribution like f of your measurement y given, and some people will use a semicolon or a bar symbol, given the parameters of the distribution, like theta or mu and whatever, your mean sigma and mu, right? So that's normally how you would describe the function. You have some function of some data y given these values. And the only difference and then there's the function. The only difference that I was describing is if you likelihood looks exactly the same, except now it's a function of the parameters given some measured data that you've seen. But the function's the same. The statement of the function is the same. It's just the order of the arguments have changed, right?
Is that the same thing or similar to taking the data that you're applying to deep learning and then getting a kind of, if not a curve fit? Like you're taking data and you're basically doing curve fitting.
Yeah. When you curve fit anything, you're trying to estimate those parameters, you know, given your data. You've got some data, I've measured it, here it is, it's there. And I've got an idea of a probability distribution, either like from, that I came up with out of the blue, or empirically from some Bayesian approach and that I'm refining. But either way, you have some probability distribution, and then you use the data to fit the probability distribution is going to be parameterized by like 1 or 2 variables, and you're just trying to find a fit for those variables that satisfies some condition, like a maximum likelihood or some other optimization condition. Keith, did you have a question?
Yeah, actually, you kind of anticipated, I think, with the total least squares extension.
Yeah.
Going way back to the very beginning with the graph that you were showing, what is a linear model?
This one, the ordinary least squares, yeah.
Right, so the question that I had as the talk was going on was, how come it's always taking the vertical distance
Yeah.
rather than the perpendicular,
Exactly, right? So I was going to put I thought about putting that picture, I have that picture here from the book, and I thought about putting it in there, but then I'm like, I don't have time to talk about it. So the fact is that this model, this ordinary least squares model, you can rewrite this model equivalently, saying I've got an exactly measured data matrix X, my unknown coefficients B, and then my observed response measurement Y, plus some error on Y, and you can say that that error is going to fit your probability distribution that you've assumed about Y, or inferred about Y from Bayesian methods. And that's one way and then, so one way to do this is to minimize, to find a value of B that minimizes that residual error subject to that probability constraint. And then you end up with these vertical lines. Just the geometric interpretation of that is this. What Keith is saying is that if you allow X and Y to both have error, in other words, we're saying, I don't know this exactly, and I don't know this exactly, but I assume they have some error that's quantifiable. So Y is now Y plus epsilon, and X is now X plus delta, or something like that. If I allow error in both of these terms, then kind of a magical thing happens. Instead of this picture, you drop instead of measuring these distances, you're measuring the distances perpendicular to the line. It's a beautiful geometric interpretation. Let's see. I actually wrote some R code.
You did not pay me to ask that question.
Yeah, so here's some R program I wrote to illustrate this. So there's our data that we were looking at before, and the dotted lines are the ordinary least squares fits that are going vertical, and that's the fit, the model line that fits the data. And in this case, the solid line is the total least squares fit with errors that are measured perpendicular to the fit instead of vertically to the fit. And that perpendicularity goes through to all the dimensions if you're in a higher dimensional than space, right? And so that's kind of a cool, why, what is the deep meaning of that? I don't know, but it is beautiful geometrically. I'm not sure how deep it really is.
As you say, that in chemistry lab, and there is error in Y, the response, and there is error in control variable.
Yeah, we used,
Very common problem.
it was very common. At this plastics chemistry place I worked at in Cuyahoga Falls years ago, we used total least squares quite a bit, actually, because of that. But only in linear models, not in only in very simple things, not in, GARCH or mixed effects models. There's no reason why this stuff can't be extended into those regimes. It's just people just haven't done it that I know of. I mean, maybe they have. I'm not an expert in total least squares, so I don't know.
Brian, one thing that struck me was you said that there may be applications of the Newton method that have problems. I thought that that there was some way to analyze this stuff using real analysis or something, and that they've already all done that. Is that not the case? Or?
Well, when you say in real analysis, I mean, be aware that there are no real numbers on computers, right? So floating point arithmetic is quite a different animal from, so for example, your arithmetic in your computer is not associative, right? So what do I mean by that? So here I'm in R. Can you see? How do I make it bigger? There we go. So I'm in, sorry, it's not R Studio, but I'm in R. So I can say, what's the common example? So like, 0.3, right?
1 divided by 3 times 3.
There we go. That's what I'm looking for. 1/3. That's 0.33333. Actually, it's even simpler than that. Like, you don't need a repeating decimal. 0.3 should be enough. 1 over 0.3 is 3. 3. No, hang on. Sorry. Now you've got me. Hang on. Let me. So this is an interesting thing. Just bear with me for one second. There we go. This is what I'm looking for. Okay, so if I... So 0.3 divided by 0.1, right? That should be 3. Is that right? That's like 0.3 times 10. And it's not, right? So that's a problem right off the bat. We've got some serious issues with math. And those aren't repeating decimals or anything. Those are like pretty easy numbers, you know. And R can't even get that right. It's not R's fault. It's the processor's fault. The thing is there's only finitely many floating point numbers. And they approximate the real numbers. And to make it even weirder, they're not uniformly distributed. Like between -1 and 1, there are twice as many floating point numbers as there are between 1 and 4. 1 and 3, sorry, between 1 and 3. So it's, or to make it easier, between 0 and 1, there's twice as many floating point numbers as there are between 1 and 2, right? Weird, right? And there's a hell of a lot more there than there are between like 1,000,000 and 1,000,001. So it starts to get really wiggy when you compute in computers. And so it's not easy to analyze algorithms, like what you're saying, to know really what's going to happen. It's very, very tricky. Plus there are all these weird edge cases involving infinities and signed infinities and 0. There are zeros with number signs on them in R, which is kind of, in floating point arithmetic, which is kind of weird. But I wanted to, there was something else. So here I am in R source code for, I don't know, 3.5, whatever. It's maybe a slightly old development version. And let's see, I'm going into stats. No, not library. I'm going to go into, here we are. So here's the Fortran routine. No, this isn't it. Oh, here it is. This is what R uses to compute GLMs, right? This is its rank revealing source code. This is written by Haka. And notice this comment line. It's pretty awesome, actually. So that's what I've been trying to do for the last 2 years, is to suggest improvements to this code. I haven't quite gotten to the point yet where I have a this is a very high quality algorithm, and I don't yet have something that is truly worthwhile to replace it yet. That's general enough and fast enough, but I will sooner, you know, at some point. It's taken a while just to understand all the subtleties of this problem. But one of my longer term projects is to actually try to fix this up a little bit, because this is a little bit of a weak spot in the R source code at the moment. It's very good, right? But it does have some issues, is all. Isn't that funny?
That's pretty amazing to see that. I guess I had wrongly assumed that with LinPack they had figured out the limits on all that stuff.
Well, no, but Haka modified the LinPack code. It's a bespoke, this only exists in R. It doesn't exist anywhere else.
Okay, so LinPack doesn't have this problem.
Well, Limpac doesn't exist anymore, but Limpac did not have this algorithm. That is right. This is something new. This is, or new as of 1994, that's stuck in R for that long. Takes a while to. Good algorithms should last a long time, you know. So this one's pretty good, but we can do better. This algorithm is why R is slow for GLMs, actually. And that's why there's that speed GLM on CRAN, is to get around this. But they didn't do as good of a job as they could have done, in my opinion. So, but to do a really good job is fairly non-trivial, right? You have to really think about it hard. I mean, like I said, I've been thinking about GLMs for years now, and I still don't know everything about them, right? It's a complicated can of worms to deal with.
When you finish your version, will there be a way to sort of override the default GLM in R so that it would pick up the improved version that you're doing?
Yeah, what Mike and I and Taylor, what we're thinking, you know, and I've talked a little bit with Martin Meckler about this, is like the long term is we're kind of thinking about, you know, something that's a drop-in compatible GLM but that is a package for a while, right? That people could make a choice to use, but have a one-to-one compatibility with the built-in GLM, and then iron out all the problems in the package world. And then once that's ironed out after a year or 2 or 3 or whatever, then maybe think about merging it into base R. Well, it's not base R, into recommended R. It's in stats, actually. So it'll be a long-term thing. That'll be a package at first, just like speed GLM, but much closer to GLM, actually. And then also with extensions to handle generalized linear mixed effects models and Garch as well. So to cover more than just GLM, like a bunch of other offshoots of GLM, actually.
You mentioned those a couple of times. Is there any reason why this wouldn't work with a generalized additive model?
No, it definitely, we talk about that in the book. I'm no expert on additive models, but GAMs definitely, a lot of these ideas would definitely go through to GAMs. Yeah, I just, Taylor wrote that section. I don't know as much about them, but you know, but yeah, a lot of these ideas, they're all just basic ideas. I mean, nothing here is rocket science. This is all basic calculus and linear. You know, first semester calculus, first semester linear algebra. Maybe, actually, this is like third semester calculus because it's like Jacobians and Hessians, right? But you know, still just derivatives. Yeah. Well, thank you all. I hope it wasn't too boring. And I don't take that badly, right? You should rely on R, right? R is a very it's a, you know, despite this, it's a testament that it's as solid as it. I mean, you know, R is a very well vetted, carefully written thing, because you can go into the source code and look at everything, right? You know, MATLAB. You have a clue what they're doing, right? Mathematica, who knows what the hell they're computing inside there. But you know, R, Python, Julia, you know, those are things that you definitely should feel comfortable using. And R, by virtue of the fact that it's just so old, right? I mean, R itself is only from the early 90s, but R is based on S, right? Which dates back to the early 80s or so. When did Chambers write it? 82, something like that.
I mean, the first version was like 79.
79, okay,
Right.
so yeah.
New S was 88, I think. So.
88, yeah. Okay. Wait, was that? No, but are you,
The blue book is like 88.
Chambers Blue Book, right?
Yeah.
Okay, yeah. Yeah. So yeah, you should have great confidence in this language. It's the reference. All these algorithms are the reference implementations that you should compare against. They may not always be the fastest, but they're almost always really solid.
So Brian, what do like Julia and Python implementations of GLM do for like this problem, for like the core the edge cases?
Yeah, so I've looked at Python. I don't know Julia so much, right? So my feeling with So Python's pretty good, right? They have you know, the code in, so one of the things with Python is there's code kind of scattered all over the place. There's NumPy, SciPy. Those are really just kind of like array libraries, like matrix, and then the real interesting stuff is in scikit-learn for the most part, right? And the stuff in scikit-learn is pretty well crafted by and large. There's some variable quality there, but they have a GLM implementation that that does like what speed GLM does. It kind of ignores numerical edge cases for the most part, which, you know, often is not that big of a problem. But they're honest about it, right? They don't really, you know, it's not like they're trying to pull the wool over anybody's eyes. In fact, in the past, not with this code, but with other Python codes, I actually literally saw this in Python once, and it made me like Python, actually. I don't really care for the syntax of the language that much, but I like the way they roll, because it's changed because they improved it. But way back, they had a Fisher exact test function in Python somewhere in like a statistics package, and they computed a very basic. They computed in a very basic way. And if you look at R's code to compute the same thing, it's very complicated. It has Fortran code from Bell Labs, like really complicated stuff. And I think, wow. But then when you read their documentation, it says, well, we only compute this basic version. If you really want to compute the full version, then you should. Then they actually pointed to R, right, in their documentation, which I commend. I thought that was very cool. Whereas Julia, at the time, this was years ago, Julia just computed it wrong and didn't tell you. Right, I didn't, and that's what made me. So I for years now, I've had this bias where I think the Python people are pretty cool for the most part, and the Julia people are pretty dumb. But that's unfair, because in more recent iterations of Julia I've looked at, and again, I don't know their GLM, but in general, the quality of their algorithms has dramatically improved over just the last few years. But when it first came out, it was arrogance and bad coding all around, right? Yeah, but again, Julia's open. At least you can look at it, right? You can see how bad it is, you know, if you really want to. But I think and that's unfair. It's much better now than it used to be. You know, Python is very good, right? The scikit-learn stuff is well documented. The code is clean. Good use of core numerical libraries, and I mean, all the stuff you're actually computing is written in Fortran, right? Nobody's using Python to do anything, right? All the core computational algorithms are done in Fortran for the most part. These days, some people like Dirk are really hot on these C++ implementations of numerical libraries, but they offer no benefit, as far as I can tell, over the Fortran codes. They're generally slightly slower. The king of numerical computing remains, to this day, the second oldest computer language, right? Fortran. So yeah, it's quite amazing, actually. All right. Well, thanks everybody. Sorry it was so little technical and boring.